Good evening, everyone. Yeah, good evening, everyone. So, today's talk in the year-long program on triangle groups, Beal information and modularity will be given by Professor Angelos Koutsianas, and he will be speaking on the Darmon's program 1. I mean, it's the first part of the Darmon's program. So I think he will give the second talk in a few weeks. So, Professor Angelos, the floor is yours.
Okay. Okay. Thank you very much for the opportunity to give the talk in this actually very. I mean, you have this semester. You have a really great talk, so it's really a great honor for me to give one of them. So today, as you can see from the title, I'm going to talk about some results and work about Darmon programs, and the new results is joint work with Imin Chen, who is giving the second talk about the Darmon program. So, okay. So I guess I know that you have already seen what the modular method is from Nicolas' talk. And since you know what the modular method is, you know that with the modular method we solve Fermat's last theorem, and after that people, mathematicians start thinking how we can attack more complicated Diophantine equations of Fermat types, like the one I have written here, the first one, and compared to Fermat's last theorem case, we can have any triple of exponents PQR. And of course, we add some conditions to a solution A, B, C that we want to determine. We want A, B, and C to have GCD equal to 1. That means the solution is private. And of course, we don't care for the case when one of them is equal to 0, and such a solution is called trivial. And the conjecture about this generalized Fermat equation, which is called Beal price conjecture, is that there are no non-trivial primitive solutions for when the exponents are greater or equal to 3. And as I say at the end, it's important to add this primitivity condition, because otherwise someone can easily find solutions that the solution of this equation. Okay. So both the primitive and trivial are two standard conditions to the solutions. Okay. Now, in the modular method, we have some work to do in order to use it. And the first thing we have to do is okay, in principle, the modular method is a method based in contradiction, which means that we have a family of equations, Diophantine equation we want to solve. We do not expect any solution. We assume there exists one, and somehow we are trying to find the contradiction at the end. And the contradiction is by comparing Galois representations, and one Galois representation comes from the geometry, the other one comes from some modular form. So some of the steps in the method require to construct these geometric objects and study its arithmetic. So the first step in the modular method is to actually obtain a Frey curve. In the classical case, it's an elliptic curve defined over a total area field, and we want to compute the conductor and the discriminant. As long as we have this, as long as we have a nice curve, we use modularity. We need to know modularity, and we also need to know reducibility of the residual representation of this geometric object. And as long as we have the previous two, we apply lever lowering, Ribas lever lowering, and we get an isomorphism between the residual representation of the geometric object of the elliptic curve is isomorphic to the residual representation of a new form. And as long as we have this isomorphism, at the last step, we are trying to find a contradiction based on the previous isomorphism we had. Okay. So for the classical case, the first 4 steps are really based on the great achievements of the second half of the previous century in arithmetic geometry. So sometimes at the end, the most difficult part is the fifth one, okay, to get this contradiction. Okay, so that was the classical case. Now, Darmon, in a work in 2000, more or less wanted to describe and explain how we can follow the same strategy to attack more difficult equations with more complicated signature for any general triple RQP. And Darmon, in order to do that, replace the geometric object we had, which was an elliptic curve, he replaces with an abelian variety of GL2 type. And now, instead of staying over Q, we have to go a little bit higher to a totally real field. And in order to do that, Darmon computes all these abelian varieties explicitly. He writes down equations, at least for the cases of signals PPR and RRP. For more complicated triples, Darmon gives explains how we can get some equations, but he doesn't actually give the equations of the abelian varieties. Then we have to prove modularity, and Darmon does this in some cases. And the time he wrote the paper, he was able to prove some other cases of modularity based on some conjectures, which are theorems now. So somehow we are able to prove modularity in our case nowadays using lifted theorems that we have now and Darmon didn't have. Now, again, we have to get irreducibility, and compared to the elliptic curve case where we have the result of measure for higher dimension abelian varieties, geometric objects, irreducibility is not known. So somehow we have to find a way how to prove irreducibility. And then the fourth step is level lowering. Again, this is something that we can do even for abelian varieties, thanks to work of Jarvis, Rai, Fujiyara, and who have generalized reverse level lowering to totally real fields. And at the end, again, as long as we have this isomorphism between residual representation, somehow we have to get a contradiction somehow to prove that this isomorphism, which all the previous theorem say that they exist, somehow does not actually exist in our case. Okay, so the Darmon program more or less says that we have to follow the same steps, but somehow things are more complicated because the geometry is harder. Okay, so one of the things that play crucial role and explain later why we add some conditions in the theorem is the conjecture of big image. And what does this mean? Okay, for the trivial solution 0, 1, 1, 1, yes, 1, minus 1, 0, I think, or no. Okay. For trivial solutions, the geometric objects we get has a complex multiplication. This is something Darmon has proved, and if we want to completely solve the generalized Fermat equations, we have actually to answer this conjecture by Darmon, which says that if we get an abelian variety over a total number field of GL2 type, which has really a big group of isomorphisms, then at some point the residual representation contains SL2FP when P is really big enough. And this is something that we actually know it when the dimension of the abelian variety is 1. this is something that based on work on Major and Darmon Merel, and this conjecture explains later, as I said, why we add some conditions, we have some restrictions, and we are not actually able for the moment to completely solve the equation, the generalized Fermat equations. Okay. So,
excuse me, I just have a
yes,
small question.
Yes, please.
So, in that proposition, is that a if or no if statement?
I'm not sure about. No, I think no. It says that if we have a trivial solution, which is I think 1 comma minus 1 comma 0, which does not give a singular curve, then this the Jacobian of that curve has complex multiplication. Okay, but it's not the other way around.
Okay. Okay. Thank you.
Excuse me, do you mean K to be the two Ks to be the same?
Which case?
The K, the letter, the field K, and
yes.
Yes. No, but you have a K which is the field of endomorphism, and you have a K which is the field of definition of the abelian variety.
Yes. For the abelian varieties I'm going to construct, it's going to be the same. Yes, in general, this ring of endomorphisms maybe contains another number field L of the dimension of degree equal to the dimension. Yes, but in this case, both are
so
the same.
It's not, when you mention Merel, it's not like the uniformity type result, or okay. All right, thank you.
Okay, yeah. Okay, so one of the things Darmon defines in this paper in 2000 is the Frey representation, and the definition is the following. He defines the Frey representation of signature PQR with respect to a triple T1, T2, T3, where these Ti's are points in the project of P1 of K bar, to be a Galois representation of the absolute Galois group of the function field of KT, where T is a variable, to a group of GL2 of F, where F is a finite extension of Fp. And we need these three extra conditions to be satisfied for the representation. The first one is when we replace GKT with GK bar T, then the representation has to be trivial, of trivial determinant and irreducible. When you take the projectivization of our rho bar, then this is ramified outside these TIs, and at the end we want the image. We want this representation to the image of the inertia to these points TIs to be a cyclic subgroup of PCL2 with order PQR respectively. Okay, remember that this TI, T1, T2, T3 correspond to PQR, okay? And this is the definition of the Frey representation of a given signature. And okay, the definition looks a little bit complicated, but what you should have in your mind is that this Frey representation is a family of Galois representation with respect to the parameter T, where T lies in the P1, okay? So as long as we have this, the reason why we define this Frey representation in this proposition, which says that if I have a trivial, non-trivial primitive solution to this Diophantine Fermat equation, generalized Fermat equation, then the representation, when we replace T with this ratio, is a quadratic twist, which is ramified outside a given set S. So this is the key. This proposition explains why we define the Frey representation, just because we can actually relate them with the study of Fermat equations. Okay, and Darmon, I will explain later, actually explains how we can get the Frey representations for a family of curves. Okay, they're going to be Jacobians of they're gonna be representations of Jacobians of some geometric objects of higher genus. Okay, but we are gonna see this in a second. So in order okay, we divide the Frey representations in two families. One family is what we call them odd representation, and the other one is even. And the way we get odd and even is the following. Let's assume that T1, T2, T3 is 0, 1, and infinity. And let's say that sigma I is a generator of the image of this I, of the inertia at this J at 0, 1, and infinity. And we have chosen this generator such that their product is equal to 1. Then Darmon explains that we can take a lift to SL2 of this sigma J, and there is a unique lift. And when the product of the lifts is equal to -1, then we say that the representation is odd. And when the product of the lifts is equal to 1, then we say that the representation is even. Okay. So as I said later, this Frey representation come from some geometric objects and are, thanks to the earlier proposition, are related to Fermat type equation. So if we take this Lejeune family of elliptic curves, which is the one that I have written here, and this Lejeune family corresponds to Frey representation of signals of PP3 with respect to the point 0, 1, and infinity, then we can see that a quadratic twist of this Lejeune equation when we replace T with AP over CP is equal to the usual elliptic curve we have seen in the proof of Fermat's last theorem, and then the representation is ramified outside S, okay, outside 2, when S, so the S, the set of primes that the proposition says, in this case, is equal to 2, and Hecke has proved that there's a unique odd representation of Frey representation of that signature PPT with respect to 0, 1, and infinity. And this is something, this last theorem is something Darmon generalized for any possible triple in the signature. Okay. So if we try to study more complicated exponents of different signatures, for example, for this talk we are going to focus to the case PPR, and later we are going to fix R equal to 5. We can see that we can describe some hyperelliptic curves, which is this one. The minus is with respect to and we are going to get from the minus, we are going to get odd representation. With the plus, we are going to get even representation.
What is reason for choosing these curves?
Excuse me?
What is reason for choosing these curves?
What's the reason? The reason is we're going to show that Frey representations with respect to this signature, PPR, corresponds to representations that come from the Jacobian of these hyperelliptic curves. This is something I will say later.
Okay.
Okay, and this is something Darmon has proved. Okay, so we have these two hyperelliptic curves, and we have which I denote plus and minus. because as I said, some of them will correspond to odd and even Frey representations. And we also denote with JR plus or minus T, the Jacobian over Qt of these hyperelliptic curves. And Darmon and in his paper, and this Top and Verbeek Gomez, sorry for the names, they actually prove that the Jacobian of these Frey curves, of these hyperelliptic curves, are of GL2 type over K, where K is the maximal totally real subfield of Q zeta R, are of GL2 type, the representation, and their mod P, where P is a prime that divides small p, representations are even and odd Frey representations with respect to signals of PPR, okay, and over the points 0, 1, infinity, okay, and and so if we, so how we relate this Frey representation with Fermat equations of signals of PPR? If AB sees a solution of the Fermat equation, then these curves, which are similar to the previous one, are just twists of the ones I wrote earlier, when T is replaced by A P over C to the R, and this is for the minus K. For the plus case, it's actually isomorphic to CR plus T over Q, again when T is replaced by A to the P over C to the R, okay? So these curves are gonna be used in order to resolve the Fermat, the above generalized Fermat equation, okay? And you can see here for so small values of R, how these equations look like, which means we can actually write down the equation explicitly. You can see that for the case R equal 3, we get elliptic curves, something that we already know here, the plus and minus case. And for higher values of R, like 5, 7, 11, we have higher genus hyperelliptic curves, okay? Then the discriminant, which is something we need later, the discriminant of these curves has some factors that has a factor of 2. I mean, the primes that divide the discriminant is 2, R, and the primes that divide A and B. And you can see here, like the classical case, the part of the discriminant that we are not actually able to control, which is the one that comes from A and B, is in a pth power. So this is quite similar to the classical case. This is something we really need in order to apply later level lowering and get finite representations, okay? And as I said earlier, regarding to the questions you asked, this for the trivial solution 1, minus 1, 0, which is a non-singular curve, the Jacobian does have complex multiplication over Q zeta R, okay? Now, as I said in this talk, we are going to focus more about the signals of PPR, but in Darmon's paper, and this is something Imin is going to talk about more, we can get Frey abelian varieties of other signals like RRP and in general for RQP. For RRP, we again have some I think they are still hyperelliptic curves, and some of them may be superelliptic. And for the more complicated signals to RQP, we get some abelian varieties we are called hypergeometric abelian varieties, and it's kind of difficult to write down equations, okay? Something else that we actually need later is that we can relate the representation that comes coming from the Jacobian of the abelian varieties, when we focus only on the R torsion part, is isomorphic up to twist to the R torsion, to the representation that comes from the action of the Galois group on the R torsion of the Legendre curve, up to twist, as I said. And apart from that, apart from the isomorphism, for the plus case, we know that this residual representation is reducible. This is something that we are going to use later in order to prove modularity. Okay, so these are two properties that we need later. And as I said, we are going to focus to the case when the significance of PPR when R is 5. And we have to add some local conditions to our solutions A, B, C. And the conditions we add is this one. That means we are looking for solutions that mod 10 are not equal to 0 for A and B. And the main result, the result from the Diophantine side is this one, which says that the Diophantine equation x to the n plus y to the n equals z to 5 does not have non-trivial primitive solutions under these two local conditions. Okay, and I may say a couple of words at the end why we add these two conditions. So what we are going to show you next is how we apply the modular method step by step, like the ones I presented at the beginning, in this particular Diophantine equation. And you remember the first thing we have to do is to actually describe the geometric objects from where we are going to construct Galois representations. And this is something, as I said earlier, Darmon has given to us, and it's given, in our cases, we have these two hyperelliptic curves, which are parameterized by the solution A, B, and C. Okay, we have the Jacobian of them, and we can put all we can replace in the previous slides R with 5, and we also get these two discriminants. And as I said earlier, the part of the discriminant that we are not able to prove is in a pth power in both cases. Okay, as long as we have this. And we have the Frey curve, we have to compute some invariants. One of them was the discriminant, which is something easy. The other one we have to compute is the conductor and the third level of the Galois representation. And in this particular case, compared to the classical elliptic curve case, things are a little bit harder, just because the geometry is a little bit harder. And I'm going to show you how, which means that things are quite different for higher genus Frey curve. And I'm going to show you how we can do that. Here I fixed the notation for later. And one of the theorems we prove is that we are actually able to compute the third level for the plus case explicitly, which is equal to R. And for the minus case, we can prove that the third level is equal to Q2 times R to the T, where T is equal to 2 or 3, up to a quadratic twist, where this x naught is a quadratic character that comes from a finite list of explicit quadratic extension of K. Okay, we are also able to prove that the residual representation with respect to J plus and J minus are both of them finite at P. This is something we need later. Okay, so how compute the conductor? How we can, because the third level is related to the conductor computation. For for the plus case, things are easy. And of course, you can imagine that the difficulty in the conductor appears when we want to compute the conductor at Q2 and at R, because for all the primes, we can prove that both of the curves have a semi-stable reduction over K. This is something that we can do it with the double root criterion, but with respect to the prime above 2 and the prime above 5, things are a little bit more complicated. So for the plus Jacobian, it's not too hard to make a suitable change of variables, this one, in order to prove that the C plus has good reduction at 2, so the conductor is trivial at Q2, and again, making another change of variables in the equation of C plus, we can actually prove that the curve gets semi-stable reduction at R when we have 5 divides A and B. And here it's R because we can do that for any R, but let's say that in our mind we have R equal to 5. Okay, so for J plus things are easy. For J minus things are a little bit more complicated. And in order to let's focus on the conductor computation at Q2. In order to do that, we have to use the fact that we have to use the Legend elliptic curve, and the fact that as I said at the beginning, the torsion, the action of the Galois group on the torsion part of the R torsion part of J minus is isomorphic up to twist to the action, to the module under the action of it's isomorphic up to twist to the torsion, to the fifth torsion part of the Legend curve. And in this proposition, we can actually show this isomorphism explicitly, which says that under the local condition, we have this isomorphism between these torsion subgroups, torsion modules, and where this X naught corresponds to extensions with respect to square root of D, where D is one of them. And the conductor, as long as we have this isomorphism, we can prove that the conductor on the right side is equal to Q2, just using Tate's algorithm. So the same holds from the left side. So we do have the conductor computation for at Q2 at J minus up to a twist, which is okay because sometimes if the conductor exponent is really, this conductor exponent is really small, it's just 1. So if in many cases the conductor exponent is really big, and when we try later to compute the space of new forms, that may be difficult in practice. So being 1, it's okay, even though we have to take some twists. That's not a problem in practice. So as long as we have computed the conductor at 2 and at all the other primes apart from 5, we know that the curve has semi-stable reduction over K, then we have to focus on the conductor at 5. And the way we compute the conductor is by explicitly determining the extension of KR over the curve becomes semi-stable. And we have two cases in this, we have 2 cases, yes, in this computation. The first one is when this quantity, which is the constant term of this GX polynomial, which is just the shift of Fx, which is the one that determines the curve. When the valuation of this quantity is greater or equal to 2, we can prove that over a totally ramified 4-degree extension, the curve obtains a good reduction. And if the valuation of this quantity is equal to 1, we have to go a little bit higher, and we can prove that the hyperelliptic curve gets a good reduction over a 20 degree totally ramified extension, which we explicitly determine. And we can prove that these both extensions in both cases are minimal with respect to the ramification index, which means that there's no any other extension of KR of degree less than the ones we write down over the curve that gets semi-stable reduction, good reduction. Okay. The way we do that.
Excuse me, is the valuation have to be at least 1, or can it be 0 as well?
No, it cannot be 0 just because we have the local conditions for A and B. When A and B, we have this condition, so this cannot be 0 actually. That comes from the computations.
I see.
Okay.
Okay, thanks.
And okay, so as long as we have the previous proposition, we can actually, it's not too hard to get the conductor, and we can actually prove that the conductor of the curve at 5 is either r square or r cube, and we can do it in two ways. One is using magma, since we know the extension over the curve gets good reduction, becomes semi-stable, then we can ask magma to compute the conductor of this, of the conductor exponent of this representation, since we know, and there are finitely many possible extensions ML, which I denote F here, and we can ask magma to compute the conductor of this representation. Someone, and that's what we did at the beginning, can try to do it in some sense by hand. It's a little bit more painful, but it's also possible. On the other hand, we can prove it with more, let's say, not using magma, we can use some results of Lockhart, Rosen, and Silverman in order to bound the conductor by 3. And actually, in the work of Lockhart, Rosen, and Silverman, they say that it can be 2 or 3. So it's the same like the one we had compute, and it's consistent with the computations by magma and by hand we did. So we have 2 different ways we can compute the conductor. And just a couple of comments about the conductor computation. There is a lot of work by many people like Dokitzer and their student Maestre and Mongan, who have developed techniques how to compute the conductor of hyperelliptic curves over local fields of odd characteristic, but for the moment, as far as I know, their techniques are applicable when I give you a specific hyperelliptic curve, and we haven't. We cannot see how we can apply these techniques and their computations when we have a parametric family of hyperelliptic curves, like in our case. That means, in other words, there is no an analogous of Tate's algorithms when we have higher genus hyperelliptic curves. But it may, I think it's worth trying to see the details of their work and see if we can actually use it in order to make our life easier. And also there's the other work of Annie and Dokitzer about the same computations when the polynomial is an Eisenstein polynomial. And Darmon had done some similar computation about the conductor using the manifold uniformization of the Jacobian, getting either similar results, getting, yes, for J plus, actually Darmon had computed the conductor, or getting some upper bounds of the conductor exponent of the curves. And both our computations and Darmon's computations are consistent. So as long as we have the curve and the invariance of the curve, we have to prove irreducibility. And we actually prove irreducibility for both J plus and J minus under the local conditions. These are the two theorems I present here. And the way we do that is just straightforward in the sense, in the elliptic curve case, we have the work of measure that we can, which is a really big result that we can actually use in order to prove irreducibility in the elliptic curve case. But for higher genus hyperelliptic curve, even for genus 2, there's no similar result as far as I know, at least. And so we don't have an analogous of measures result in genus 2. So we had to do somehow, we have to deal the reducibility property. And the way we did that is just straightforward. In other words, just say, let's say that the Jacobian of, let's say, the Jacobian of J minus is not, the representation of J minus is not irreducible, which means it's irreducible and is written in this form, where this theta and theta prime are two characters whose product is equal to the cyclotomic character. And as long as we focus, we restrict our attention to how this theta and theta prime acts on the inertia IP, then we can prove that the sum of these characters restricted to the inertia is isomorphic either to chi p plus 1, where chi p is the cyclotomic character, or psi p plus psi p to the p, where this psi p is a fundamental character of level 2. So these are the two cases. This is something known. And for the third case, we can assume that theta is, or theta prime, one of them is ramified at every prime above p. And as long as we have this assumption, we can use a little bit of classical theory to prove that in this case, we get the contradiction of reducibility when p is big enough. Big means greater or equal to 7. And the second case corresponds to the case where both theta and theta prime ramify at some point above p. And in this case, with some criteria we develop, which I don't actually, because it's quite technical, I haven't written down here, we are able again to prove that the reducibility property fails when p is greater or equal to 7. So in both cases, at the end, irreducibility is something we are able to prove. And then we have to prove modularity, because for modularity and irreducibility, we are going to apply Ribes level lowering. Modularity for the J plus case is not too hard, using the fact that J plus has multiplicative reduction R, and the representation is ordinary. Moreover, the residual representation at R is reducible, something I mentioned at the beginning. And then as long as we have these two properties together with the lifting theorem of Skinner-Wiles, we can actually able to prove modularity for the J plus Jacobian. And
this is
for the
old, no? Skinner-Wiles?
Excuse me?
Skinner-Wiles was old, I think, right?
Say it again, please.
Skinner-Wiles result is old, I think, right?
Yes, I think.
A recent result.
No, not recent. I think. Sorry. I think it's that paper in. IHCS in
97 around.
yeah, I don't remember that. Yes, it's around 2000.
Yeah. Okay.
Yes, it's for example, I think modularity is proven for J plus. Yes, I have written. It's proven by Darmon, and Darmon's paper is in 2000, so the paper is earlier.
Yeah. Okay.
Okay. So for the J minus, we are also able to prove modularity, and the way we do that is proving that first we focus on the residual representation at R, and we prove that it's absolutely irreducible, and we can extend it as a Galois, as a representation over JQ, and as long as we are able to extend it at JQ, we can use Serre's modularity conjecture, which is a theorem now, and prove that that the representation of the extension is modularity, and then by base chains, a cycle base extension theorem, we can prove that the initial residual representation at R is modular, and as long as we have modularity at of this residual representation at R, we can use Tander-Lifton's theorems to prove that to prove modularity of J minus, and we have this statement here, which is the modularity. And as long as we have modularity, we have all the ingredients together with theorems of Ribes-Leverloh of Hilbert new forms thanks to Jarvis and Rayai in order to actually get the proof of the theorem. And here I just mentioned that for small primes that we don't have reducibility yes, we don't have reducibility. These small cases have been resolved by others. For n equal 3 is a result by Krauss. For n equal 5 is Fermat's last theorem. The case n equal 7 has been done by Niels Bruin, and the case n equal 4 has been done by Bruin, and the case n equal 7 is a result of Dachman and Zygzak. So in our case, so for us, we can assume that P is greater or equal to 11, and we have all the properties we need in order to apply the elimination step, the final contradiction step. And as I said earlier, as long as we assume that P is greater or equal to 7, and for the case 2 does not divide AB and 5 divides AP, then we use the J plus Jacobian, and from irreducibility modularity we can apply Leverloh in Hilbert new forms, and we get this isomorphism where between the residual representation of our Jacobian and the residual representation of some new form, Hilbert new form G over K, and the level of this new form is R, and doing the computation in magma, we can actually get that this space is empty, which gives the desired contradiction at the end. So for the J plus case, everything it's okay. Now if we go to the other case where 2 divides AB and 5 does not divide AB, then we have to work with the J minus. And remember, in the conduction computation, we had to take a twist of J minus. So I denote by G the twist of J minus by this chi naught character. Chi naught is given, lies in a finite list of characters. And for this J, we still have reducibility and modularity, because reducibility and modularity does not depend on the twist. So from level lowering of Hilbert new forms, we get an isomorphism between the residual representation of J and a residual representation of a new form that comes from a space of fixed level of this one, of level 2 times r to the t, where t is equal to 3. And magma is able to compute both spaces of new forms for these levels. And in order to get a contradiction at the end, we are doing the standard argument modular method. We just compare traces of Frobenius. And because of the previous isomorphism, we have this conquest relation between the trace of Frobenius of the Jacobian and the new form for primes different for primes q different of 2 and 5, and we define this product, and by all the previous assumptions, we know that P has to divide this big product, and if we make a right choice of this Q, and as a result of this product T, we can actually get a bound of P. And if we get many Qs and the GCD of all these T's, we actually get a small bound of P. And in our case, everything works very well for all the characters chi naught. And we have chosen Q to be 3, 7, 11. And as long as we take GCD of all these T for all new forms and for all characters, we're actually able to prove that P has to divide, has to be smaller than level, which is the desired conclusion and contradiction we have at the end. And this is more or less the strategy for this particular Fermat's type generalized Fermat equation. And yes, thank you for your attention.
Yeah, thank you very much, Professor Angelos. So the floor is open for questions or clarification.
Yes.
Any doubts? Yeah, please feel free to ask.
What exact modularity theorems you used in your results?
Sorry?
Which modularity lifting result you used in your results?
It's thanks to the Diamond and I don't remember the second name. Yes, the real, yeah.
This 2014.
Yeah, I don't really remember the statement, to be honest, but from that paper by Diamond and his co-author, I don't remember the exact theorem.
Okay.
Hi, Angelos. I have a quick. Oh, sorry, Devendra. I'm interrupting you. Go ahead.
So, and did you mean that the measure type results are not available for the abelian variety? Which results you mean?
Where I mean, what do you mean? I mean, the modular method.
The reducibility part of the program, you said that the measure type results are not available. So, which result did you mean basically?
You mean the curves?
Yeah.
In Darmon paper, Darmon is able to, where is that?
There's 5 steps now. Just go on the very first step.
No, it's later, right? Yes, here.
Yeah.
Okay, for signature RRP, this is something that Imin is going to talk about. Darmon actually gives away how, and explicitly describes how we can get these curves and the corresponding Jacobians, and the same for RRP. But for more complicated triples, Darmon says, okay, this we can attach some abelian variety, which in the literature is called the hypergeometric abelian varieties, but it's does not give an explicit way how to construct them, right? He doesn't even write them and does not actually give a way how to construct it. So yes, I mean, I don't know how we can get these things.
Okay.
Yeah,
Okay,
and
Kunal.
I mean, it's worth someone trying to find equation of them, even for some small, like R equal to Q equal to, I don't know, 5, 7, and P varies. Yeah.
Okay, thanks.
You're welcome. Rana?
Hi, Angelos. Thanks for the nice talk. So I have a quick question about PP7 or PP11. And ideally by Darmon's program, yeah, things should fall in place similarly. But where does the main difficulty lie? I mean, you can find those abelian varieties according to Darmon for RRP. But is the difficulty lies in finding the level loading results, or what kind of difficulties are there for?
Okay.
Where is the main difficulty? I know there are several difficulties, but what is the main crux of the matter?
Okay, in general, one of the main difficulties in this approach for the moment is to prove to compute conductor and probably prove modularity. But I think conductor computation it can be hard if you are trying to do all the computations. I mean, if you don't, especially, I mean, if you don't really want to get this twist, for example, for the conductor at 2, the computations may be hard just because we don't have this algorithm. But in principle, things will work fine in principle. If you replace R with 7, then the difficulty will also, you will also have a difficulty when you are going, you may do all this hard work, proving modularity, reducibility, blah, blah, blah. And at the end, when you are trying to compute the Hilbert new forms, just because the extension, the degree of the base field where you're doing the new forms computation is going to be really high. Like in case R equal 5, the degree is 2. At 7 is 3. At 11 is 5. Okay. Mm-hmm. Then you may stack on the computation of the Hilbert new form, which is something completely it's an independent problem. So yes, I think the main difficulty is going to be probably at the end in the computation of Hilbert new forms. You may not be able to compute them. Otherwise, I think we have developed enough some techniques, and of course there are space for improvements. Replace 5 with 7, 11. It will not make a big difference. Maybe there are some technical points you have to, because there are many technical points around which I haven't actually mentioned, but in principle, you are going to be able to overcome all these difficulties. Yeah.
Okay. And also one more quick question on this, have you considered the generalized Fermat type equation for signature PP5 in this case, for A x to the P, B, y to the P, C to the 5, where A, B, C are composed of some small primes, or you have some control on.
Okay, one of after this project, one of my next projects is to completely write down, study the equation you mentioned, the generalized. I mean, the generalized Fermat equation of signal PP5 with coefficients. And to get an analogous results like Mike Bennett and Skinner and the other one with Bennett, Vatsal and
Yazdani.
Yazdani, yes, because it's the natural next step, right? For I don't know how. I mean, PP2 has been used. I mean, the machinery Bennett and Skinner have developed for PP2 has been used for by many other authors. I guess the same is going to be done. Is going to be done. Yes, happen for PP5. I mean, in any case, it's the natural next step for us. Yes.
So yeah, I mean, if that is the case, maybe that might be useful. The problem we are looking at for a Selfridge curve with exponent 5, that might like boil down to this, right? So for solving generalized PP5 curve, equation, right?
And actually, I mean, if you add some coefficients in front of x, y, and z, you may be able, you will be able to completely solve some of the equations, just because you won't have these trivial solutions that pop out.
Mm-hmm.
And they don't give you non-singular curves.
Okay, makes sense. Yeah, thank you. That's all my question. Thank you for your answer.
Thank you.
Thank you. Thank you again for the great talk.
Yeah, I just have one more question. So in your main theorem, you have some assumptions on A and B, like 2 divides or like 5 divides.
Yeah, okay. Where's the main theorem? Okay, yes.
So, like in the remaining cases, what do you expect to happen? Like
Okay. The reason why we add these two conditions is just because we are not able to solve it, but it's something deeper. Something deeper happens here. For example, when in the case PP2 and PP3, which were solved by Darmon and Merel, in order to the reason why we add these two conditions is because we want to avoid the trivial solution 1, minus 1, 0. Okay, because this one is an abstraction. So adding these two conditions, you actually avoid them. Okay, and the reason why we are doing that is just because, as I said, and probably I didn't say it completely, in the case PP2 and PP3, we have these results by Darmon Merel, which explain how the Galois representation in the complex multiplication case behaves, okay? In a non-split and split Cartan, and they give some conditions to the J invariant, and probably you know about that. Okay, so for genus 2 curves case, we don't have an analogous of Darmon Merel's results. So we cannot somehow isolate this abstraction. And in order to get something, at least, in the direction of Darmon's program, we want somehow add some local conditions in order to isolate this solution. And that's why we add these two these two local conditions. That's why I said to Prana earlier, if we are trying, if we study the general Fermat equation with coefficients, and you add somewhere here, you add, I don't know, constant that does not actually give you a solution, you may be able to completely solve the question. Yeah, okay. That's why.
Thank you.
And sorry, and in order to get an analysis of Darmon Merel, the result is something that people, I think, have thought about that, and it's something not trivial. Okay, it's not something that we could do and we didn't. It's something really deeper. Okay.
Yeah, I've gone through the Darmon's Merel at some time, but that's what I was wondering, why that approach was not taken. This seems to be Okay, there seem to be some more deeper reasons, I think.
Yes, but I think, okay, one, who gave the talk? Okay, wait. And this is, okay, and this is what I said, and this is related to this conjecture. Okay? For example, if you prove that this conjecture is true, even for some p, really big primes p, then you can actually prove, completely solve the, at least for big p, we are going to be able to solve, to answer the PP5 generalized Fermat question. And I think, yes, this one have said a couple of things in his talk, I think.
It is kind of bounded conjecture.
Excuse me?
It is kind of bounded conjecture.
Yeah, yes.
Uniform bounded conjecture.
This conjecture.
Yes.
Yes, I mean, this is a conjecture by Darmon, and it says that, okay, if P is really big for GL2 type abelian varieties, the projective residual representation is really big.
Yeah,
So
it
if you
has a large image. Yeah, that's what it says.
Ah, yes, sorry, yes, sorry, I didn't understand. So if we have this conjecture, then we can use it in order to isolate the solution 1, minus 1, 0, just because in that case we have complex multiplication, so the image is not going to be big enough. That's the whole argument, more or less. But we don't have it. We don't have the conjecture.
And are there any upper bounds for this CK, just even conjecturally?
I don't know. To be honest, I don't know.
Okay.
But I think in this talk, I had a look in the slides. This guy says something even conjecturally, I mean, assuming modularity actually, for extension of odd degree, was able to say that this thing holds. I had a look of the slides yesterday, or maybe 2 days ago. Yeah, but in any case, this concept is also nice. Somehow generalized Darmon-Merrell's theorem, which is not trivial at all.
Right. Yeah, of course. Yeah, are there any more questions or comments? Okay, if not, let's thank the speaker once for his wonderful talk.
My
Thanks,
pleasure.
Angelos. Thanks,
You're
Narasimha,
welcome.
for sharing.
Yeah.
Thank
So
you
if
very much.
preprint
It was
is
a nice
out,
talk.
Angelos.
We are planning to, I mean, the paper has taken longer than it had to. We are going to, hopefully in a couple of months, we are going to upload something in archive.
Okay, great.
Yeah, I think we are, a year ago, I would say that we were not close to the end. I think now we are close to the end. Yeah, for this problem, for this project.
Yeah,
If you don't,
nice.
if you don't mind, I can stop sharing, okay?
Yeah, okay.
And congratulations.